Alright, everyone. So today I'm going to be starting a new series actually on an introduction to linear algebra. So we're going to be starting off with vector spaces, and I'm basically going to follow the book Linear Algebra Done Right by Sheldon Axler. So um, this video will be the first in that series. So when you think of a vector, you're probably thinking of perhaps an arrow in 2 or 3 dimensional space like this. And you know that you can add vectors together, like maybe if we have a vector like this, then, oh, that's a really bad drawing, hold on. If you can add vectors, sort of like so. You can also multiply them by a scalar, like in this case 2. But what we want to do in linear algebra is there are more interesting vectors than just arrows in 3-dimensional space. We can generalize by thinking about some of the properties that vectors have and creating a definition based on these properties. So I guess it's a good place to start. Let's start with defining operations. So, for example, we have addition. An addition is a function, so it maps some element. So let's say we have 2 elements in a set. It's mapped to an element u plus v. So 2 elements get mapped to 1 element. So it takes in 2 elements from v, and it spits out an element in v. So for example, if we have elements 1 and 2, perhaps the addition function may spit out 3. Then we also have, oh, hold on. Scalar multiplication. Okay, I don't know why it's glitching out like that, but it assigns, let's say we have some lambda in F, which is a field, and for our purposes, you don't really need to know what a field specifically is, though it will be helpful if you do know. Just think of it as like real number or complex number, because that's what we're going to be using most of the time. And if we have element v in the set V, then we get an element lambda times V, which is also in V. So it maps, it takes an element in V and it takes an element in the field and maps it to an element in V. So now let's define a vector space. A vector space is a set, so it's a set V with addition and scalar multiplication. I'm just going to use those 2 symbols as shorthand, such that the following properties hold. So, properties of a vector space. Commutativity. So if we have u plus v, then it is equal to v plus u for all u and v in the vector space. The vector space is also associative. So if we have u plus v plus w, that equals u plus v plus w grouped in a different way. And if we have A times B times V, that's equal to A times B times V for all U, V, and W in V, and for all A and B in the field. There is also an additive identity in a vector space. So that means there exists an element which we'll denote with 0. There exists an element 0 in the vector space such that V plus 0 equals V for all V in the vector space. Also, for every vector in the vector space, there exists a vector W such that V plus W equals 0. We also have there exists an element 1 in the field such that 1 times V equals V for all V in the vector space. And then last but not least, the vector space has distributive properties. So we have these sorts of, they're very similar to distributive properties that you're probably familiar with from high school or even before. For all AB in the field and all UV in vector space. So that's a lot of properties. So if we think about this in terms of arrows, let's say we have U, and then this is V. This is U plus V. If we have V and then U, that's V plus U. So you can see how in the special case of arrows in Euclidean space, commutativity holds true. And if you go through the rest of these, you'll see that all of these end up being true. For example, this 0 in V would just be the 0 vector. So the arrow with 0 length. And if we have a vector, let's say a vector like this, maybe there's a vector in the opposite direction, which we'll denote by negative V. And as you can see, if we add them together, we get the 0 vector. That's sort of what we're dealing with here. So we call elements of a vector space. So elements of vector space are called vectors or points. And we say that we have a vector space over F if F is the field we're considering. Furthermore, a vector space over R, the set of real numbers, we call a real vector space. And as you would expect, if we have a vector space over C, which is the complex numbers, then we have a complex vector space. Now a bit of notation. Let's say S is a set, just any set. Then Fs denotes the set of functions from S to F. So we can define addition and scalar multiplication on this set as well. So for instance, if we have two functions like so, then that's how we define f plus g. And if we have lambda in f and f in fs, then we define lambda f by simply multiplying the result of f by lambda for all x in S. So now let's get to some proofs. Our first theorem is the following. A vector space has a unique additive identity. That means there is only one additive identity. So, how would we prove this? What we would want to do is, let's say we have a vector space with two additive identities. The goal is to prove that those two identities are the same. So, let's say we have 0 and 0 prime are both additive identities. Then, we need to use some of the properties that we know. So, remember, this is an additive identity. 0 is an additive identity. So, this holds true. Furthermore, because vector spaces are commutative with respect to addition, we can swap these around. And remember that 0 prime is an additive identity. So that means this is simply just going to be equal to this. And therefore, these two identities are exactly the same. Therefore, no matter how many supposed additive identities there are, you can always prove they're the same via this method. Therefore, a vector space must have only one additive identity. So that's a pretty simple proof. Let's move on to the next one, where so the next one is that every element in a vector space has a unique additive inverse. So that means no two elements share the same additive inverse, or no two different elements share the same additive inverse. So, or actually, in this case, sorry, I misspoke. No element has more than one additive inverse. So, suppose we have a vector in the vector space, and W and W prime are additive inverses. This is essentially the same song and dance, okay? We want to prove that W and W prime are the same. So, because the additive identity property, we can write this. And we know that because W prime is an additive identity, or additive inverse of V, then V plus W prime equals 0. So we can write W plus V plus W prime, because this is equal to this. And by the associative property, we have that it's equal to W plus V plus W prime. And we know that this equals 0, W plus V equals 0, because W is an additive inverse of V. So strangely enough, W equals W prime. So that's the end of our proof. So a little bit of notation. When we write negative V, that is the additive inverse of V. And if we write W minus V, that is simply W plus the additive inverse of V. So furthermore, when we write V, for our case, it will simply just be a vector space over F. So there should be like no ambiguity about that. Let's prove something else. So we want to show that 0 times V equals 0 for every V in the vector space. So let's take 0V. We know that 0 equals 0 plus 0 in both real numbers and complex numbers. So, and also in fields as well, but you might not know about that. So just pretend we're working in real or complex numbers. And by the distributive property that we mentioned before, we can distribute the V. So we have 0V plus 0V. So if we cut out the middleman, we have 0V equals 0V plus 0V. If we subtract 0V from both, we get 0 equals 0V, which is what we wanted to prove. Furthermore, if we have a vector 0 and we multiply it by a scalar a times 0 equals 0 for all a and f. So no matter what number you multiply the additive identity by, it still remains the additive identity. And the way we prove this is we consider a times 0. Remember that by the additive identity property, we have 0 plus 0. And by the distributive property, we have a times 0 plus a times 0. And then if we add the additive inverse or subtract a times 0 on both sides, we get 0 equals a times 0, which is what we wanted to prove. The last thing we want to prove, these very basic properties about vector spaces, is the following. So we have the scalar -1 times vector v that equals the additive inverse of v for all v in the vector space. So what we want to prove is that, we need to show that v plus -1 times v equals 0, okay? So here's how we're going to do this. V plus -1 times v, we know by the fact that v equals 1 times v, so we have 1v plus negative 1v. And by the distributive property, or the reverse of that, we have 1 plus negative 1 times v. And no matter what field we're in, 1 plus negative 1 is going to equal 0. So we have 0v, which equals 0, as we previously said before. Therefore, because this is true, we know that negative 1 times v is an additive inverse of v. So that's just a very short introduction to vector spaces. I hope this video was informative if you're looking to learn a little bit about linear algebra or vector spaces, and I'll see you in the next video.